He's an assistant professor of electrical and computer engineering at the University of Michigan, Ann Arbor, where he's leading the Complex Engineering Systems Laboratory. He obtained his PhD in electrical engineering computer sciences from UC Berkeley in 2022 and was subsequently a postdoctoral researcher at Caltech. His current research work, he is interested in all aspects of cyber-physical systems, emphasizing formal methods and AI that support their compositional design and analysis. As you can imagine, it's very relevant problems that Professor Insert's talk is going to be. With that, the floor is all yours. Inigo.
Okay, so good morning, everyone. Thank you so much, Aditya, for the kind introduction. It's truly a delight, to be with you today and to have this discussion about formal system design. And I'm very much looking forward to having conversations and hearing your impressions about this. So the conversation is going to be about, okay, how can we prove that the systems obtained by interconnecting pieces are going to have desired properties? So we want to have these formal properties of our systems. And, the motivation for that is, of course, the fact that today we have trouble in system level design, right? So in automotive and aerospace, we hear about, this news of recalls and recertifications happening. And, if we ask ourselves the question of, or at least part of the reason why this happens, many people from both industry and academia point out at the fact that, today we lack, theory and tools that will allow us to prove that that the interconnection of systems will have desired properties. One way to put this is to say that, in our various engineering disciplines, we learn how to design components in isolation, but we don't have theories, to analyze interconnections. Something that we can see as a reflection of this fact is, what I would, this expression of digital engineering, right, that we see in the systems industries. So I was looking for a definition of this term, right, and Terry Hill, who leads this effort at NASA, has this very nice description of what we mean by digital engineering. So he says that, so this is all about building products with, better performance, better schedules. How? By integrating multiple models and tools, right, in this along a seamless flow of information. So this idea of doing something for the integration of components to build systems is very central to this notion of digital engineering, right? And if we think about someone from academia telling us something along the same lines, so Joseph Sifakis, who is very well known in formal methods. So it speaks about the need that we have to design a science for system design, and then he has these very lofty words about it. So he tells us that the impact that this could have is comparable to the quest of scientific discovery in the natural sciences. So as we think about requirements or problems that any science of system design should enable us to address, we can think about the following kind of super high level challenges. So the first one is that whatever mathematical or theoretical framework we use to think about system design, it should better allow us both to express and to manipulate requirements coming from heterogeneous sources. So in a complex system, we are going to have sitting at the table, people who will be coming from manufacturing and financials, from safety and security, from legal and certifications. So our theory should allow us to express all of it, right, and manipulate it over the lifetime of the product. So this is what we will call requirement one. The second one is that today in the systems industries, there is a significant amount of friction between system integration and component suppliers, right? So we can, these two parties, the integrator and the supplier, enter into a business relationship through the concept of a legal contract, okay, whereby they are bound in this business relationship. So we can dream about a situation in which these two parties, okay, in addition to exchanging this legal object, they could also exchange a technical object, that we can call a technical contract. And this notion of contract is going to come up a lot in our discussion. So whereby, the system integrator could know that if the supplier implements this contract correctly, this part is going to integrate in the system and the system will have desired properties. So this is what we can call also a challenge that we'd like to address. The next one is the fact that in our complex systems, we use heterogeneous forms of analysis to address various pieces of the cake, right? In the sense that that anything having to do with thermals and structures will use a form of finite elements. Anything having to do with energy will use some form of the circuit theory, and label transition systems for software analysis and so on. So the question is, after we reach conclusions about the various pieces, how do we stitch our conclusions together to say something about the system? So contracts have been proposed to address these issues in a coherent framework. So contracts are going to be both an algebra and a methodology that allows us to deal with two very high-level system-level problems. The first one is what we can call system integration. So with system integration, what we mean is how do we understand the whole from our knowledge of the parts. So contracts as an algebra, we are going to have an algebraic operation called composition that we are going to see in action very soon, that is going to give us the data of the entire system from the data of the parts. With contracts, we can also do the opposite operation, meaning this. Suppose that instead of going from the pieces to the whole, you want to go from the whole to the pieces in the following way. Suppose that you want your system to satisfy a certain specification, and there is a piece of your system that you already developed. So contracts have an operation that allows us to identify the specification of the missing piece that you have to add to your system so that it does what you want it to do. Okay, so this is what we mean by system integration. Contracts also have something to add regarding a notion that we can call dealing with multiple viewpoints. So the idea here is this. So at the same company, we can have multiple groups of people who are not working on different objects, but on the same object. And then one group may be in charge of developing a functionality specification. Another one may be in charge of developing a power or timing specification. So how do we bring all this data into a single contract? Is going to be accomplished by an algebraic operation that we are going to call merging. So these are the two high-level tasks that we are going to address, and we will see this in action very soon. I would like to mention that in addition to this algebra of contracts, over the last couple of years, we have been working on the development of a tool that we call PACTI. So at PACTI.org, we can see information about this. So this is a way in which, as we are doing system design, we can use a Python environment in order to analyze our systems using contracts. And up to this point, this contract-based design using PACTI has been applied to problems in cyber-physical systems, which we see on the left-hand side of this slide, and synthetic biology, which is on the right-hand side. So regarding cyber-physical systems, if you look at the top left of this slide, we have applications to space mission design led by NASA JPL, multi-agent robotics, and also to autonomous cars. And regarding synthetic biology, the problems that we have been addressed have dealt with how can we ensure the performance of genetic circuits in the midst of resource competition. So so this is PACTI. So the topics that we propose to discuss in our meeting today. So in order to start thinking about contracts, we are going to introduce them by considering a design problem proposed by JPL and how we needed a different form of analysis to address early questions in the design process. Then we are going to consider additional algebraic operations in a case study on quantifying the robustness of the perception components in a self-driving car. Then we are going to say something about, okay, what is the actual mathematics that we are talking about? That is going to be our point 3. And then we'll discuss other applications to control systems and to security. Okay, so let us begin our discussion by considering this case study proposed by JPL. So the idea is this. Imagine that we are developing a spacecraft that is supposed to satisfy a rendezvous mission. So a rendezvous mission means that the spacecraft is going to go meet some object of scientific interest, such as an asteroid, and we are going to make measurements and report them back to Earth. So we are going to understand our spacecraft as doing one task at any given time. So at any given time, our spacecraft can be in DSN mode. That means Deep Space Network. So this is the communication infrastructure used to talk to our devices in outer space. So when the spacecraft is in DSN mode, what you do is you look at Earth, okay, and you exchange data with Earth, right? So SBO means small body object. That means that the spacecraft is pointing at the object it is meant to study, the asteroid, and is going to deploy its scientific instruments in order to acquire measurements from this device. TCM stands for trajectory correction maneuver. So this is engaging our actuators in order to approach the object that we are studying. And charging means, okay, we look at the sun and receive maximum energy from it. So the in the very early stages of our mission, there are two high-level questions that we are going to to try to address. So the question looks like this. Imagine that we have a schedule of these modes of operation of the spacecraft. Okay, so first you charge, and then you send data to Earth, and then you make measurements, and some schedule is given to us. So the two high-level questions are going to be, can this particular spacecraft, record and transmit all observations as set as the mission objective by the science team in this mission. Okay, so can we accomplish this? And the second question is going to be, can we complete this mission, with our battery level never falling below a certain threshold? So we do not want to lose access to this device in space. So two super high-level questions, right? Very early on in the mission. What our colleagues from JPL tell us is that at this point, we would consult in order to move forward with the development of the spacecraft. We would consult, the systems engineering handbook of NASA in order to, understand what are the next steps in our development. Okay, so we are so early in the design process, okay, that we are just specifying our mission objectives. So what would happen next would be to start engaging the multiple stakeholders in this mission in order to refine our high-level requirements into detailed requirements for each of the parts, so that we can eventually build this spacecraft. So one difficulty that sometimes we run into, as expressed to us by our colleagues, is that this process can involve very deep feedback loops, in the sense that we take our mission objectives, decisions are made early on about the division of the requirements for the various components. We start developing detailed simulation models. We carry out analysis at the very detailed level, and we figure out that there are problems, and sometimes we have to reconsider some of the decisions that we made early on. So the question here was, can we implement an analysis procedure that would involve a much shallower feedback loop, okay, in such a way that we could get early information about the multiple approaches that we could take to implementing this device. Now, the big requirement that we are adding from the beginning is that in this analysis, we do not want to use simulation models. Now we can say, well, simulation models are the workhorse of engineering design, right? But the reason we are abstaining from using simulation models at this point is, you could say, threefold. So the first is, we are so early in the design process that simulation models may not be available at all, right? They just have not been developed yet. So the second reason is that, by definition, detailed simulation models, can be used by very few experts in each application area. So, your very detailed thermodynamical models, well, there are some experts that can access them. And the same thing is going to happen with our EM models, with our circuitry, with all the various pieces. So in the very early stages of design, we want an analysis mechanism that someone with a system level view can approach, without becoming an expert in all these various subjects, okay? And the third requirement, or the third motivation to this, is that detailed simulation models, usually take significant amount of software and hardware setup to be used, and they provide insight into very carefully specified conditions. We would like an analysis mechanism that can cover a wide range of options at once. As you can imagine, we are going to be using contracts for this. So let us start discussing the notion of a contract. Okay, so assume guarantee contracts are going to be formal specifications that come in two pieces. So first of all, formal specification means, of course, a specification with mathematical content, a specification that a computer can understand. And these are specifications that come, as we said, in two pieces. So one of the pieces of the contract is going to be what we call the guarantees, and the guarantees represent what is this component giving us, if we add it to the system, right? And the contract is also telling us what are the assumptions that this component makes on its context of operation in order for it to deliver its guarantees. So we can think about a contract as the mathematical analog of a component datasheet used in engineering design. And this is the first connection that I would like to point out. Okay, before we were talking about, okay, there are a few approaches to compositional design. So notice that the idea of a contract is motivated by the current practice of engineering design. So today in engineering design, we use components that come with datasheets, and the datasheet is the fundamental object that we use in order to interconnect multiple objects. All a contract is doing is mathematizing that notion. So as we see in the top right of the slide, a contract is really a pair of statements, assumptions, guarantees, where the assumptions and guarantees have mathematical meaning. So an example of that, of a contract that we would use, for example, in a security application, would say something like, under the assumption that at most 30% of my location sensors are compromised, we can still guarantee that we will reach the destination with a probability of 1 minus epsilon for some small epsilon. So this is the fundamental object we are using. Now, contracts are useful, okay, not only because they allow us to express specifications, but because they come with a rich algebra that allow us to manipulate these specifications and relate the information of components to the information of the entire system. Okay, they also have a notion of order that allows us to identify when a specification is more difficult to implement than another one. Okay, so there are two operations that we are going to be using in our considerations of the spacecraft introducing a couple of slides ago. The first operation looks like this. Imagine that you have a system, as shown in the bottom left part of the slide, a system that is understood as an interconnection of these three components. All we know about the components are their ports, meaning their inputs and outputs, and for every component we know its contract, meaning its mathematical datasheet. So every component tells me, under assumptions A sub I am going to give you guarantees G sub I. Okay, so the operation of contract composition will allow us to go from that kind of diagram to a diagram that places a box around that entire structure and happens to have top level inputs I1 and I2 and a top level output Y. So we will see this in action very soon. Okay, so this is requirement, the operation number one. We call that composition. The second one that we are going to be using is an operation we call merging. That looks like this. So on the bottom right part of the slide, you see this diagram in which the outer box now represents one component in our design. So this can be, for example, the outer box can be a microprocessor that we have in the design. The internal boxes represent contracts that we have written for various aspects of the microprocessor. We call them viewpoints. For example, one of your viewpoints can be a timing specification for the microprocessor. Another box can be a power viewpoint for your microprocessor, and so on. So what the operation of merging will do is that it's going to generate a single contract that knows everything about your component. It knows about timing and about power and so on. The use of this operation, we have found that it's very helpful at the point of specification capture. I mean, from our software experience, we know that we people are less error prone when we enter our data in pieces. So, when we write small routines that we can understand, for example. So what the operation of merging allows us to do is to write specifications by focusing exclusively on power or on timing or on functionality, and then we let the algebra do the job for us. I would like to show you very quickly an example of these operations at work. So let us consider composition first. So composition, remember, gives us a system out of pieces. Suppose that you have the system shown on this slide, which is obtained by interconnecting two components. So you have component M and M prime with those kinds of inputs and outputs. Okay. So all that we know about these two components is going to be their contracts. So for component M, we know that if we make the input less than 2, okay, the component guarantees that its output is going to be equal to its input. And the second component tells us that if we make the input less than 1, then it guarantees that it's going to make its output equal to its input. So we don't know anything about M and M prime. We don't know how they are implemented. All we know is their interface specifications. Okay, we could have a complicated mathematical model inside of M. But here's the question that we want to ask. Imagine that we build such a system and we give it to a user. What would be the contract that we would tell our user is obeyed by our system? Okay, so this is really a question that we can brainstorm right now, right? So just by looking at this example, we can take a look at the two contracts, and come up with an answer. But I want to repeat the question just so that we are on the same page. So the question that we are asking is, given the contracts of these two pieces, imagine that we build such a system and we give it to a user. What is the data sheet that you tell the user is obeyed by the resulting system? Now, notice that the user only wants an interface specification, right? So if we reason about this example for a few, for a couple of minutes, we are probably going to reach something like this. So we will say, if you make the top level input I less than 1, you are going to get an output O prime, which is equal to the top level input. Okay, so, and I would like to mention a couple of virtues of this system level specification. The first is the fact that it only uses variables I and O prime. So the internal variable O completely disappeared. And the reason is the user probably is not interested in that internal variable O, right? The user wants to know, okay, so how do I use this at the interfaces? I am not interested in the internals of this. Okay. So this is virtue number one. The second one is the fact that we are creating this new constraint that says input less than 1. Okay, this is a constraint that did not appear before, so it doesn't appear in our existing data. But the reason we are creating this input less than 1 is so that if we operate under this restriction, the two components that we interconnected are going to be operating within their assumptions. Right? That is why, and we want to do that because only when operating by respecting each of the components' assumptions, we know that the components will give us their guarantees. Okay, so this is what we can intuit from this example. And okay, so we mentioned this tool PACTI before. So the way that we will do this in PACTI is using the code that is shown on the right-hand side of the slide. So we can verify that lines 1 through 5 represent the contract for the first component. Lines 8 through 12 represent the contract for the second component. Okay, and then in line 15, we are asking the tool to obtain the contract of the entire system, obtained by this interconnection. And in this case, the tool gives the contract that we obtain by using our intuition. So are we on the same page regarding composition? So composition allows us to go from the pieces to the entire system. So a second use for composition that I would like to point out. Imagine that you have the same interconnection as before, okay? But now we are going to change the contracts slightly. So the first contract says, if my input is less than 2, I promise my output is bounded by a number. And same contract for the second component. We can go through the same exercise as before. Okay, we can say, okay, imagine that we build such a system and we give it to a colleague who will be a user. We can invoke the tool that we used before. We can define our two contracts, and in line 16 of this code, we can ask the tool for the composition of the two contracts. Okay, in this case, notice that we get an error, and what the tool is saying is the following. The tool says, look, I want to compute a system level specification that does not mention the internal variable O. As we discussed, the internal variable O is irrelevant for the user who wants to use this at the interfaces. Now, what I found remarkable is that the tool is saying, I find it logically impossible to eliminate this internal variable O. What I found remarkable is that the fact that there is a logical impossibility to eliminate the internal variable O points to the fact that we may have a bug in the system. And the bug is that we may send in 3 units into a component that is asking for a maximum of 1 unit. I like to point out that this is not the kind of bug that we are guaranteed to catch in simulation. In simulation, it could have been the case that O was equal to 0. Okay, if O was equal to 0, you pass the first check, you pass the second check, and you have a successful run. I mean, of course, in this example, we can say, well, but I can think about my corner cases. Sure enough, but if you have 10, 20 components, thinking about corner cases means thinking about all the permutations, right? About all corner cases you could have. So the point of this is that by using the contract as the object of computation, we are catching all these corner cases at once without even thinking about them. Okay? So this is related to a question, where we were discussing before about the fact that, we could implement M and M prime correctly, but when we interconnect the system, we can get something that we don't like, right? So this is exactly what is being caught here, right? The fact that, there are incompatibilities between components that composition can reveal. So that being said, okay, let us go back to our example. So remember that, we were building the spacecraft that, in which we were given a certain schedule, and there are two high-level questions. Okay, can we record and transmit all asteroid observations, and can we do this with our charge not falling below a certain threshold? So this is how JPL approached this using the ideas of contracts that we have introduced. So they said, okay, over the course of the mission, we are going to keep track of a few quantities of interest. We're not going to call them state, but we would call them state in dynamical systems. So these quantities of interest are things like how much charge do we have in our battery, how much scientific data have we gathered, how much data have we sent to Earth, and what is our relative distance to the object that we are supposed to study. Okay, so these are high-level quantities that we are interested in tracking in our analysis. And this is what we defined as as atomic contracts. So let us take a look at this at one of these boxes. How about box A in the slide? So box A is going to represent what a certain task, take for example charging, what a certain task is going to do to one of our quantities of interest when we execute that task. Okay, so imagine that we are charging, so we are only going to think about what charging does to our state of charge, for example, quantity of interest. So the contract that we are going to write for the power viewpoint of the charging mode of operation is going to contain two input variables. So one input variable is going to be the state of charge that is being handed down to us when we begin executing this mode of operation. And delta T is an input variable that tells us for how long are we executing this mode of operation. Okay, V exit represents the value of our quantity of interest after we are done executing this task. Okay, so the contract looks like this. The contract we end up writing looks like this. It is a relationship between the quantity of interest that we see on the y-axis and the duration for the execution of the task that we have in the x-axis. When delta T is equal to 0, just sitting on the y-axis, we have the value that is given to us for that quantity of interest. That is going to be an assumption for our mode of operation. Okay, so if we want to do trajectory correction maneuver, we are going to assume that we have certain amount of charge, okay, in our battery. When delta T is different from 0, we are going to provide a guarantee on what our task is doing to that mode of operation, okay, after that certain amount of time. And notice that what we have is a bound, is an affine bound for the output variable that depends on the input variable and time. This doesn't mean that our dynamics are affine. It only means that our dynamics are bounded by affine bounds that we have a priori. So remember, we are generating one of these contracts for each mode of operation and for each quantity of interest in over the course of this mission. So what happens next? Every mode of operation is going to have several of these viewpoints, several of these quantities of interest. There is going to be one contract for power, one contract for scientific data gathering, one contract for our ability to approach the object that we are studying. Remember, these are contracts that apply to the same design element in our system. Therefore, we are going to use the merging operation to generate a single contract that knows everything about power and about scientific data gathering and about our ability to approach the asteroid. Okay, and we are going to get one of these contracts per mode of operation of the spacecraft. Okay, so now we have characterized the 4 modes of operation that we had to start with. So what happens next is the following. Remember that we had a schedule that was being provided to us. Okay, so this And what we wanted to do was to analyze whether our spacecraft would satisfy our mission requirements by following the schedule. So at this point, we have a contract for each mode of operation in our spacecraft. We know what our spacecraft does when it is charging, when it is in TCM mode, and so on. So now we can do contract composition in order to obtain the specification for the entire mission as obtained by following this particular schedule. And from the conversation that we had a couple of slides ago, there are two potential outcomes to this composition. Composition is either going to not work. Okay, that means that there can be an incompatibility between our modes of operation in the mission. In other words, at some point there may be a task in our mission whose assumptions we are not always guaranteed to satisfy. Okay, in this mission. So this will be, a way to reject potential schedules or spacecraft. But the other alternative that we have is that we get a successful composition, meaning that there is a way to be sure that this particular spacecraft is going to satisfy our mission requirements. And in that way, the spacecraft is going to be 100% guaranteed, okay, to satisfy our mission requirements, provided, of course, that we had correct data for each of the modes of operation. So what we have here is, some analysis that our JPL colleagues carried out regarding their computation time. So what you see here is that, and I just want to point our attention to to this second row of this table right there. What this is saying is that we are able to analyze 200 different spacecraft in schedules that have about 100 tasks. That's what this 20-step means. So schedules with about 100 tasks in an amount of time in the order of a couple of minutes on a modern workstation. Okay, so what this is telling us, right, is that we can iterate over 200 different spacecraft and understand whether they are feasible to complete this particular mission. So in other words, what we learned in this example is that by using this contract-based analysis and these techniques, we are getting closer to the shallower feedback loop, or at least there's a path to implementing the shallower feedback loop that that we were looking for initially. Okay, so this point one, served us two things. Of course, it allowed us to discuss this space mission. It allowed us to see what kind of analysis mechanisms are not quite there today, but where contracts may have something to add. And then we saw two operations at play. Right? We saw the operation of composition and the operation of merging being used. So what we have next in our conversation is a different case study that is going to showcase a different operation on contracts that we can use in order to perform an important system level analysis. And it goes like this. So let us talk now about self-driving cars, okay, for a few minutes. So imagine that we are designing a self-driving car. We are understanding our car as an interconnection of just a perception component and a controller. Okay, so let us, to keep things simple. So the question that we want to address is, how should we specify our perception component? So we could say, well, a priori, that's a fairly non-intuitive question, in the sense that if we think about the perception component as an object that takes as input images and generates as output classifications. So for example, you take an input, an image, and then the perception component tells you whether there's a pedestrian or there's an obstacle in front of us. What the formal methods community has extensively used up to this point is the idea of using confusion matrices of the perception components. So you will say something like, okay, if there is a pedestrian, in my image, what is the likelihood that the perception component will tell me that in fact there is one? Okay, so this will be something like a true positive rate. So the question that we want to ask ourselves is, what kind of true positive rates for detection should we require from perception? A priori, we don't know whether we should require 1 minus epsilon for a very small epsilon, or whether we are okay with 80%. So for example. So let us see how we can go about analyzing this using the ideas we have been discussing. So, okay, so we know what a contract is. We know that a contract is a pair, A, G, okay? In our conversation so far, we discussed the operation on the bottom left of the slide that goes from the pieces to the system. What we are going to do now is the opposite. We are going to use an operation that goes from the system to one of the pieces. So if you pay attention to the diagram that is on the bottom right part of the slide, the outer box in that diagram represents a system that we want to build. And imagine that we have a specification. We know what we want our system to do. And inside that system, there is also a component that we know for sure we are going to be using in this design. So the question that we want to answer is, what is the most relaxed contract that we have to assign to the missing piece so that the composition of the two contracts inside is a valid refinement of the top level specification? In other words, how do I fill this hole that I have in my system? So quotient is going to give us a specification for the question mark that we have in the slide. So let us now see how we can use this. So again, let us come back to our self-driving car. The diagram that we write is, imagine that there is a car approaching an intersection and there is a crosswalk. And in that crosswalk, there can be a pedestrian, or there can be an object that is not a pedestrian, or the crosswalk may be empty, okay? So we want to see what specification we impose on the perception component. And as we said before, we think about our system as just perception and controller. So, okay, as we said before, thinking about a specification for perception directly is not super intuitive. However, data that we can definitely use to write a specification is a system level specification. For example, certification authorities can give us information about the probability of failure that our system can have. So in this case, what we use as a system level specification is the probability of being safe, that the system is safe. And the box that we represent is one that receives as input the visibility in the environment and that outputs the probability that our vehicle is safe, where safety for us is defined in some temporal logic formula. And let's see. So the contract that we write looks as what is shown in this diagram. On the y-axis, you see that we are writing a relation between the probability of being safe and visibility. So visibility is visibility in the environment. If the visibility is very high, we are going to be very demanding with the probability of being safe. If the visibility degrades, we are going to allow the probability of safety to degrade gracefully. We are going to place, of course, an assumption on the visibility that is going to allow us to say, well, if it draws by too much, then we are outside the assumptions of the system level contract. Now, using, our example is simply has three controllers instead of one, because we use different controllers according to the situation that we have at the crosswalk. Either there's a person or an object that is not a person, or it's empty, but the idea is exactly as we just discussed. So for each of the controllers that we have in our system, we can use statistical model checking in order to compute a contract that relates the probability of that controller being safe to the detection rate of the perception component. In other words, each controller is going to have a specification that tells me, if my perception component, is telling us the truth, then the probability of being safe for that controller is going to be very high, and it can degrade, very gracefully otherwise. So each of our controllers is going to have one of these specifications. So the situation in which we are now, it looks as follows. We have a contract for the entire system. We have contracts for each of the controllers inside, and then perception is our question mark, which is the situation that we had before. Okay, so our diagram looks like that. The three controllers can be composed in order to generate a single box for the controller component in our car. The specifications of safety for the system can be merged in order to have a single contract for the entire system. And after we do that, what we have now is a specification for the system, a specification for the controller. We can now compute the quotient operation in this system. And we are going to that, by doing that, this is going to give us the most relaxed specification that we have to place on the perception component for our system to work. And it's going to look like that. This is going to be a relation between the detection rate of the perception component and the visibility. So what is attractive about this design procedure is that if we are the system integrators, at this point in the design process, we are free to give this perceptions contract that we computed to the perception expert. And we are guaranteed that if the perception expert implements this correctly, our system is going to work. So this is benefit number one. This is something that we will call independent implementation. This allows us to independently implement all the pieces in our system. So the second benefit is the fact that the contract that we are giving to the perception expert is defined only at the interfaces of that object, detection rate and visibility. In other words, we as system integrators do not need to provide information to the perception expert that is not directly relevant to the implementation of that component. In other words, all the trade secrets that belong to the rest of the system are not going to appear here, okay, in this specification, which is also helpful for the perception expert because that person is now not burdened by unnecessary details to the implementation of the component. So all the details about this are contained in pacti.org that we discussed a few slides ago. So, this case study, covers that notion of a quotient, right? Which is this idea of filling a hole in the system. So now that we have discussed contracts, we saw them, in action in a couple of case studies. The question now becomes, okay, so what are the mathematics of these devices that we are considering? So we'll dedicate a couple of slides to that question and to defining them formally. Contracts are defined like this, mathematically speaking. So the input that we need to define contracts is going to be a Boolean algebra of specifications. So the way to understand this Boolean algebra is that this is the language that we use to express specifications in our system. Okay, so notice that in our examples, we were using linear inequalities in order to express our contracts, but we can use anything, any logic that has Boolean semantics. So given that Boolean algebra, the contracts are defined as follows. The contracts over the Boolean algebra B are going to be given as pairs A, G of elements of our language of specifications B, satisfying the constraint that we have on the right-hand side. So such that A or G is equal to true, okay? And the fact that we have pairs A, G is very likely, very intuitive at this point in our discussion, but the constraint may be a little puzzling, right? Why do we require this A or G equals to 1? That constraint is imposing assume guarantee semantics on the pairs A, G that we are using, okay? So notice what happens when the assumptions are 0, in this case. If the assumptions are false, your guarantees are forced to be true, okay? Which is, imagine what happens in a legal context if we do not satisfy a party's assumptions. If someone's assumptions are not satisfied, then we would say that that party is not liable to deliver their guarantees. This is exactly what is happening here. If the assumptions are 0, then guarantees are 1, meaning that whatever the component is doing is within spec because we do not have the right to expect anything from that component. Okay, so this is imposing this assume guarantee semantics. Now, contracts have a notion of order, which is as shown in this slide. It's we can spend some time looking at this, but what this notion of order is saying is that a contract is more difficult than another contract. We call that refinement when the guarantees are more difficult or the assumptions are easier to satisfy. Okay, which makes intuitive sense, right? You know that a task is harder if the task itself is more demanding or whether you are asked to do the same task in a wider set of environments. Right? So this is the notion of order for contracts. And there is an operation called the reciprocal that is quite important in the algebra. But what I want to point out about contracts is this. What we are going to see in this slide is that all the known binary operations on contracts can be obtained as a mathematical exercise from the definition that we saw in the previous slide. So in other words, in order to obtain composition and quotient and merging and all of this, we do not need to introduce additional axioms on the theory. Everything follows from its own definition, which means that the theory of contracts is extremely compact, right, as a mathematical structure. So, and the way that works is as follows. The notion of order of contracts that we just discussed gives rise to the operation of disjunction and the operation of conjunction. So this is what we can call the logical side of contracts. And the operation of disjunction and conjunction happen to have a notion of duality that was in the previous slide. So duality is the glue that brings everything together in the algebra of contracts. From the operation of conjunction, by using the notion of tensor products of commutative algebra, we can get the operation of merging, which we used before in order to bring these multiple viewpoints together. By duality, we can get the operation of contract composition, which is the operation that we use in order to relate the information of the component to the information of the entire system. If you remember, so now we have disjunction, conjunction, and merging and composition. Okay. So I am hearing. Hello. Okay.
Yeah. Hi. Okay. I think it should be muted now. Somebody.
Okay. Perfect. But you can hear me okay, right? Thank you. Okay. So
yes,
so we have. Thank you. So we have these four operations. Okay, so we obtain merging and composition via tensor products. So remember that composition is an operation that builds, and we had an operation that takes things apart. The operation of quotient is obtained by using the notion of right adjoints of category theory. And merging also has an adjoint called separation. So the adjoint operations are ways of undoing whatever the operations on the left-hand side of the slide do. So the operations on the left-hand side are constructive. The operations on the right-hand side are, undo the operations of the left-hand side. Okay, so turns out that duality is preserved in this, for separation and quotient. Disjunction and conjunction also have optimal ways of undoing them, and they also happen to be duals of each other. So the purpose of this slide is really to note the fact that that the algebra of contracts is incredibly self-contained. So from the definition you can get all the operations directly. Okay, and we know how to compute in closed form all these operations on contracts. And something that was learned quite recently was the following. One question that remained was, look, the definition that we are using of contracts is shown, okay, on the top of this slide. So the question was, is this an ad hoc definition, or is this mathematically well defined? So using tools from category theory, it was shown that this definition of contracts is canonical in the sense that contracts are the functor that locks two algebraic categories in place. So this is adjunctions of functors is, I would say, the de facto tool in category theory to prove the well-definedness of structures. So this was a surprise, right? That tells us that we are claiming that we are doing compositional system design. So the question that we had to address was, well, are we building the software tools on solid mathematical ground? And this is telling us that indeed, contracts are motivated from practice, motivated from mathematics itself as well. So these are the operations and what we know about the algebra. So now we are going to change gears a bit, and regarding two topics that are very much ongoing work, and where some early results have been obtained. So the first is, well, how do we apply this to dynamical systems? Okay, these ideas of contracts, and a first application of this looked as follows. So most control systems for bipedal robots and quadrupeds and many other systems are layered. Okay? So in the sense that we have a layer of planning, a layer of trajectory generation, a layer of low-level control. So the question that we had was the following. We said, look, we have very good theory, very clean theory to analyze each of our control algorithms independently. However, a problem that we normally encounter is that when we go to implement our control algorithms, our implementations normally contain artifacts that are usually not expressed in our mathematical analysis. And these artifacts may indeed break our analysis. For example, timing missynchronizations between the various algorithms. Okay, you may have an algorithm that is running on a very fast clock, another like MPC. I'm sorry, in a slow clock like MPC. Another algorithm that is running on a fast clock, like a feedback linearization on a different processor, and then their data rates don't match, and so on, and those interactions can break our system. So so something that we have done is to express our trajectory generation and our various, let me just go to the slide, is to express contracts for trajectory generation and for low-level controllers, and prove that if we implement those controllers correctly, then our entire system is going to have desired properties such as stability. Okay, so this is a fairly recent work that used contract operations to prove the stability of control systems. So another area that is of very high interest to us is compositional security. Course. So in compositions, I mean, the idea here, right, is that we want to develop cyber-physical systems to satisfy all these constraints simultaneously. We want them to be safe, secure. We want them to satisfy manufacturing and performance requirements. But the work that is ongoing right now in security is that the contracts that we defined previously, and I will go a bit faster on here, but the contracts that we defined previously are fundamentally incapable of expressing properties that are of relevance to security properties. So, and the technical term to use here is that in order to deal with some security requirements, we need something called hyper properties. So hyper properties are logical statements for which we need higher level of expressivity than what we can obtain from traditional logics. Okay, so an ongoing effort for us is to develop a theory of contracts that can manipulate hyper properties in order to carry out this compositional security. And there is early work on this, but this is very much ongoing. Okay, so that being said, let us summarize our discussion today. Okay, so we spoke about contracts. Now the first question is, so what do we gain by using contracts? So the first benefit that we reap, right, is that we think of systems and subsystems in terms of their specifications, not their implementation details. So the conclusions that we reach are going to hold for any implementation that adheres to the specification. Something else that we have found to be a benefit is that contracts make assumptions first-class elements of the theory. So we have to explicitly state what every object assumes from its environment in order to work. And in our experience, we have learned that operating on assumptions is considerably less intuitive than operating on guarantees. For example, you may remember the simple interconnection that we considered early on in our discussion, right? It was these two components in series, and we use our intuition to compute the contract of the system. So I can, our experience in considering the hello world example for the quotient operation is that we get confused very, very quickly when thinking about the assumptions of missing components. So anyhow, so the point is that assumptions are considerably less intuitive than guarantees. Something else that we have learned is that assumed guarantee contracts enable us to scale, compositional reasoning to large designs, as we saw in the examples before of JPL, and the algebra has several design relevant operations. And something also to consider about contracts is what they give us and what they do not give us. So what contracts give us is assumed guarantee reasoning so that we can relate the properties of the parts to the properties of the whole. So contracts give us system level analysis and design capabilities, but they do not replace anything. So contracts come to add, not to replace, in the sense that at some point we are going to need to check whether a component satisfies a stability property or a thermodynamical property or a security property. In order to check whether the component satisfies that, we are going to be using tools from each of the respective disciplines, right? So such as control, security, and so on. So that being said, what we discussed has been a collaboration with a wonderful group of colleagues and friends, and this has we're also very grateful for the support of many institutions. And that being said, I'm very grateful for your attention and happy to discuss any comments or questions that you may have. So thank you again.
Thank you, Inigo. Now
Sure.
we can open the floor for questioning. Please go ahead. I can start in this case. I have the quick question regarding, so thank you so much, Inigo. It's a great talk and made a lot of sense. In terms of the contracts, is there any flow between components regarding contracts where one, say the downstream component or an upstream component has a contract, which is a function of the downstream component's contract?
So the question was feedback interconnections.
So the flow of contracts
okay.
between components. So where the one component's contract is a function of, say, some other component's contract, or because in your diagrams the flows were on the inputs, outputs, the ports, but not that maybe one the contract of, say, the perception is a function of the contract of the controller based on what the controller can do, and vice versa. So is there a compositionality on the contracts also between the components?
Okay. So let me try to rephrase your question, Aditya, and you can tell me whether we're on the same page. So contracts represent the interface specification of components, right? That we have in a system. I agree that the examples that we showed, had a data flow, kind of interconnection. So is the point that we should discuss further cycle interconnections, as in feedback and so on, which we can have in many systems.
Mm-hmm. Yes.
But okay. So indeed, because what I was going to add there, right, is that precisely one of the benefits or one of the objectives that we seek in using contracts is to specify components independently. So we very much don't want a contract itself of a component, to be defined as a function of another component, because what that does is that affects our ability to develop reusable components, right? If every time that I write a contract, I need to change it according to the properties of some other component, that will be a hindrance to reusability of components. I want to have my contracts in such a way that they are just defined, and then my analysis tools should tell me, this is the system, this is how you should use this in the system, right? Which is what PACT is doing right now. So
I see. Okay.
So what I'm trying to say is that the contract itself of a component, that we should probably leave that alone, right? And then now, but I mean, you have a perfectly valid point, which is the one of interconnections, and then let's see, cycle interconnections and feedback and so on, which are all over the place in control systems, right? So indeed, the example that we over which we went quickly regarding the control systems, there is feedback in there. So there is the trajectory generation, the low-level controller. They have a feedback.
Exactly.
They have a feedback interconnection about them, and we use the same tools. Okay, what I should say is that we use the same algebra in order to compute, the composition of the two contracts and so on. PACT for the moment has some limitations with respect to the kinds of interconnections that you can have. It allows us to have feedback interconnections, but it imposes some restrictions that are not essentially part of the algebra. So there's a difference between the tools that are there and the algebra. The algebra is indifferent to the form of interconnections that we use.
I see. Okay, and I can also imagine where the contract does not change, but the contract is like a map. So the map does not change, the mapping, the function, but it can take in different inputs to provide this. The contract is not changing. It's just its particular instance changes. But that makes sense. So thank you so much.
Exactly, and then something that I'd like to say about that, right, is that a contract, more than thinking about it as a mapping, an idea that I think is helpful to me is to really think about it in as relations, right? Because what we want to say, right, is that my output is somehow bounded by whatever is going on at the input and so on, right? Because if you give yourself that ability, then I mean we have uncertainty everywhere. Uncertainty coming from our knowledge of the models, the let's see, tolerances of various objects and so on. So you are immediately able to handle that.
Okay.
But if you do that, like the NASA JPL examples that we saw before, right? So in those cases, our contracts were affine bounds, and those affine bounds come from our inability to nail down exactly what the value of our charging rate is, or who knows what other parameter.
That makes sense. Thank you so much.
I have a question. Hi, Inigo. Very interesting talk. I learned a lot. I have a quick question on this. Are there some sort of like, so in my head, the way I perceived it is that the contracts allows you to have this sort of it helps you with specification and things. So like I think my question is coming towards the point that you hinted, like stability or something. When if I provide a specification like say subsystem A is stable, subsystem B is stable in itself, and if I connect them together, will the entire composition or merging would be stable and something? So is there, I believe you said that is an ongoing work, and so are there any properties of these assume guarantee contracts that essentially work very well with these affine structures, but not with something of that hyper properties, so-called hyper properties that you said? So I just wanted to get some more insights there.
Okay. No, it's a rich question, Vivek. So let's see. So let me say something about this example.
Yeah.
So this example is very much along the lines that you're discussing, actually. So what happens in this case, the motivation was to say this. We say, imagine that we have this layer controller, and we have two parties who are implementing this layer controller. Okay, so somebody is implementing MPC, somebody else is implementing the low-level controller. Not only that, but they are actually working on different processors that need to communicate. So what we want to do is to provide a contract to the MPC expert. We want to provide a contract to the feedback linearization or trajectory following expert, and we want to generate contracts that behave in such a way that if they implement the contracts correctly, the system will be stable. So that's and then the form that it took a significant amount of reflection, to come up with what should be the right specifications that we should write for MPC and for the low-level controller that would guarantee that their independent implementation, it gives us the system level specification, but also that the contracts themselves are completely self-contained. In other words, the MPC person has all the information they need, right, in order to move forward with this. So I think that addresses your that is in the direction of your first point, right? How does this relate to control? And I think that this is a beginning in the sense that there's a lot more to do. Distributed control, for example, right, and all of that. Something that I want to say about that too, right, is that the mindset that contracts give us regarding system level design is that every component is like a lemma, right? And my system is like a theorem. So every component becomes a logical statement that says, under these assumptions, I give these guarantees. So contract composition is like computing a theorem for us. So I find that interesting because in computer science there exists a notion called the Curry-Howard correspondence that says that that a computer program can be understood as a proof of a theorem. So this also makes system design theorem proving, right? So it's very suggestive, to think about that. So, okay, so I think that that addresses the point on directions regarding applications to control and so on. The second point that you brought up was, what are the limitations on these affine functions with respect to the properties that we can express, right?
Yes. Yeah.
Okay. So let's see. I need to be more technical in order to address this. The place where you exactly need to have hyper properties is when the formula that you need to verify involves quantification over multiple behaviors. So let me expand on that. So a lot of formulas that we care about in our systems, only require you to quantify over a single behavior. For example, safety. In order to call it a day and to say, my system is safe, you can go behavior by behavior of your system and you say, yeah, this was safe, this was safe, this was safe, this was safe. And as soon as there's one that is not safe, you say, my system is bad, right? Or well, my system does not satisfy this property. Stability is the same. There are properties for which you need to quantify over more than one behavior in order to determine whether your system has that property. So security gives us a lot of those instances, because in security, for example, what you want to say is, if I am a user that doesn't have high-level privileges regarding a system, then in 2 different times that I use the system, if I give it the same inputs, I should see the same outputs. So what that prevents us to what that allows us to catch is data leaking from secured areas into my unprivileged visibility. Okay, so now. So you need hyperproperties to get those more expressive requirements. So I would say that security is a very strong motivation to go there. But before we go there, there is a lot that we can do at the single behavior quantification. Okay.
I see. Okay. Yeah. Can I? Just maybe one small follow up, and then I can let other people.
Just quickly, Vivek, we have 2 people waiting.
Okay, then maybe I can circle back. I'll circle back at the end. Yeah.
Okay, perfect. Yeah, we have Sandeep and Irene have raised their hands. Please go ahead.
Yeah. Hi. So in your example of the rendezvous, the system goes through this multiple modes, right? Now, when you're transitioning between different modes, your assumptions can change for each component twice. So is it true that when you're computing this contract, you have to consider all possible modes? And what can happen is it can provide infeasibility because you're combining all possible modes. Rather, as an engineering solution would be to have some sort of safety monitor or some sort of barriers put in when going from mode to mode. Is that something which Factory does provide, or do you also incorporate these things?
Okay, excellent question regarding that, Sandeep. So let me go back to here. Okay, there we are. So the form that this case study took is that we assumed that there was a planner that was giving us a sequence of tasks that the spacecraft was supposed to follow. And then the analysis became, let us compute the contract for each of the modes of operation. And if we have the contract for each mode of operation, we can get the contract for the entire mission. Okay. And then if we get something successful, then we know that this particular spacecraft, meaning the one that we obtain by having this communication technology and this battery charging technology and this scientific instrumentation, this can satisfy the mission objectives. Okay, so there was not a search of plans. So we assume that planning was done externally to this. Okay, and the outcome that we get here is that if we get a successful contract, we are 100% guaranteed that if we implement the tasks correctly, okay, this spacecraft is guaranteed to be successful, right? In order to satisfy this mission. So this is the form that this analysis took. Now, regarding your point about barrier functions and all of that, and let's see, something that we can consider about contracts, right? It's look at what we know about our system so far. What we know about our system is that, okay, our analysis holds as long as we implemented correctly, right? Each of our modes of operation and so on, because this is data that was given to us, okay, to start with. Right. Now, we are using these contracts in the very early stages of the design process. But what can happen next is that they can accompany the entire design process all the way to deployment, because now you can put monitors for the assumptions in your actual system that can tell you, hey, by the way, you are beginning to operate this guy outside its assumptions, which means that the analysis that you did, doesn't hold anymore. So now you can start blinking a yellow light or, calling the attention in some way. Right? So PACTI itself, will not give you something like, a barrier analysis and those things, but it is compatible with them in this very natural way, right? Because you can use them in order to monitor.
Okay. Thanks. That answers my question. Thank you so much.
Irene had a question. Irene, please go ahead.
Yeah, so if we have time, so thank you very much. This is very enlightening, and it's probably one of the best contract talks I've heard from non-contracts V&V person. I'd like to go the other direction. What if I, for example, can you accommodate the scenario where one of my component behaviors, specifically performance, gets better over life cycle because I'm learning something, right? By that is not necessarily necessitates, but it potentially alters the requirements of other components, making relaxing certain requirements, etc. Right? Is there a way to accommodate that within the contract mechanism? the way it's set up now, that something may change later for the better, not necessarily for the worse, and then you want to take advantage of it.
Right. Thanks so much, Irene. That is a great question. This is not something that we have addressed directly, but the way that I would imagine this going is as follows. The contract algebra itself, right? This is, I really think about the contract algebra as the algebra of compositional system design, right? So in the sense that, okay, we are given a Boolean algebra of the specifications, and then, you know, we can do composition on the contract. So the algebra itself, right, is going to relate properties of components to the properties of the system and so on. Something that I could envision can envision happening in this situation is that, you know, at some point we can analyze the system using the information that we currently have available. So we would say, well, I know that this component is, maybe my impression of this component is too conservative, right? And then as we operate this particular system, you know, over time, there's perhaps some learning or something like that in which we can actually update the contract. Okay, now we can redo our contract analysis in order to see whether we can use a different component in a different mode of operation that is going to squeeze more performance out of the entire system. That is entirely possible. If you remember, in one of our earlier slides, you know, we made the comment that contracts are really two things, you know. So there is one side of contracts which is exclusively algebra, and we can use the algebra however we want, right? So, you know, we can use this algebra as, you know, we can use contracts as runtime monitors, as we were just discussing. So the scenario that you are bringing up, you know, is something that for which, you know, the algebra of contracts, yes, indeed, you know, it will play a role somewhere. And we will need to develop a methodology that, you know, uses it in the right way. So, for example, you know, what I can envision is occasionally we recompute our system contract based on what has changed in the components, and then we can see, right, whether we can do whether we have new capabilities as a result of the increased performance of a certain component. But does that answer, Irene?
Yes, it does, and it also, I think, opens up a potential to use this set of tools for system trade-offs when you're actually designing the system originally, component by component, right? So thank you.
Thank you so much. Completely agree with that. Yes, sometimes we think about the situation in which the system engineer, you know, can figure out that there is, you know, that if one of the experts gives me a contract that is making it very hard for another contract to operate as part of the system, then we can have that conversation and we can see, look, you know, if you relax your assumptions in this way, then it will make it considerably easier for this other component, you know, to be implemented and so on. So I think that can be an enabler for those kinds of conversations that, you know, for which today we don't really have analysis capabilities that can do that, or at least there's no computing that supports that.
Okay, so if we're just following up on Irene's comment, so is that possible where you could foresee that this design of at the system level, given the contracts, if that can be cast as an optimization problem where each component's contracts are variable within a fixed bound, and so you are trying to find out if there's a feasible set of contracts to make the system level do what we want in feasibility, and also then, if possible, then optimize the overall system level performance.
Okay, so it is possible that the algebraic operations are already doing that, and let me explain what I mean by that. So, because you know, we didn't talk at all really about you know, how these operations are implemented and so on. You know, there is a significant something I like about this topic is that it brings together, you know, computational logic, optimization, and many you know, angles to look at specifications. So let me say something about optimization. When you bring two components together, you know, the two contracts that we composed that we had before, and then we interconnect them to build a specification for the system, the contract composition has the algebraic property that it is the smallest contract that is obeyed by composing implementations of your two contracts that you are composing. So all the algebraic operations are actually defined in terms of an optimality criterion. Similarly, the quotient operation is defined as the most relaxed contract that you can place into this hole, pretty much, that you have in the system. Okay, so
I
so
see.
so,
Okay.
so from that perspective, as you are saying, well, I have a new component. Let me reconsider. If you compute the quotient, well, you already computed the largest thing possible, which means that if for some reason you don't like the quotient because there can be a predicate that it's uncomfortable or something like that, which sometimes happens. Then, if you make a refinement of the quotient, you still have a specification of something that is going to fill the hole for your system. So it brings a different mindset really of how to think about specifications in system design. Yeah. But optimization is embedded into the algebra.
Yeah, it makes sense. Thank you so much.
Yeah.
I believe it. Do we have any other, Vivek? Did you have a question you wanted to follow? Okay, thank you
no,
so
I
much
think,
again.
Yeah. I'm just saying that my question got answered in the discussion, so no follow-ups.
Okay, okay, good. I will thank you to the speaker again. Inigo, there's again excellent talk. Please do send me email me the slides, and even if you forget, don't worry, I'll bother you in a bit to get the slides myself, and we'll post the talk and the slides on our website and share the link with you. Again, thank you so much.
No, thank you. Thank you to everyone for your attendance, and you have a wonderful weekend.
You too. Okay, bye-bye.